Hey, in this video, we're going to be talking about graphing exponential functions. And it turns out that these are actually pretty easy to graph for a standard exponential. So something that looks like f of x equals a to the x. To determine the graph, we only need 2 points. So this is a bit easier than the polynomials we've graphed, where we need to have all the roots and the y-intercept. So let's just start off with the graph. And we'll start the graph with the 2 most important points. First, the first important point is the y-intercept, which is what we get when we plug in f of 0. And so if we have some exponential, a to the x, also we're going to note that a is greater than 0, then f of 0 is a to the 0, and any positive number raised to the 0 power is just 1. I'll make a little mark for 2 and start our graph. So this is going to be our graph of f of a. So then we have 1 here. So our y-intercept for an exponential is always 1, unless it's scaled, shifted, or stretched, or some other transformation. But when it's f of x equals a to the x, the y-intercept is at 1. The next point we plug in is at x equals 1. The reason we do this is just an easy value to calculate. We have f of 1 equals a to the 1, which is n. For this graph, let's say a is greater than 1. So a is some positive number, so a is bigger than 1, so at 1, we have a. And I guess we're doing green dots, actually. All right, so then we just need to figure out what the rest of this function looks like. And we can plot points. But generally, the idea is that if a is greater than 1, then the function is increasing. So, because if we keep raising a to bigger and bigger powers, it's going to get bigger. And we've seen that it grows extremely fast. So the graph looks something like this, where it starts to shoot up right away. Unlike rational functions, there is no asymptote. So it looks from this drawing like there might be an asymptote, but there's not. It continues out till x gets to infinity. On the other side, if we're plugging in a negative number, then we have, let's say, we'll go back to black text first, but we plug in f of -1, f of -2. F of -1 is a to the -1, which is 1 over a. That's our rule about how we define a to the -1. F of -2 is a to the -2, which is 1 over a squared. So it's like this behavior where we're going to be dividing by bigger and bigger numbers. And so we're dividing by these huge numbers as we go in the negative direction, so it flattens out, but never passes 0. And so this is what our graph looks like when a is bigger than 0. Or sorry, when a is bigger than 1. So if we have like 2 to the x or e to the x or 3 to the x. All right, so we'll do another example when a is negative. Or sorry, when a is less than 1. If a is less than 1, then we still have our same y-intercept at 1. And we have another value at a, 1. And a is going to be a bit less than 1 in this case. All right, so the interesting thing to note here, though, is that if a is less than 1, and we also, for these, need that a is greater than 0, we then have that a looks like a fraction. So f of x equals a to the x, which equals 1 over a to the minus x. And now this is some positive number, or sorry, some number greater than 1, right? Because we took a number less than 1, divided 1 into it, so we end up with something positive. I.e., if a is 2/3, then 1 over a is 3/2. So it's something like that. So now we have this number that's greater than 1. And right here, then this equals, this is like a reflection across the y-axis because we have that negative in front of the x. It's one of our transformation rules. So as we plug in huge, big values, big and positive values of x, we're decreasing now and going to 0. And we're increasing on the other side. So it just looks like a reflection. And actually over here at -1, so this point at -1, we get 1 over a. So it's just a reflection across the axis. All right, so that's all there is to graphing. These are the parent functions. So if we had something like f of x equals 2, 2a to the x minus 1, then we know how to graph that just by stretching and doing a vertical shift down. That'll be our standard way of approaching these. So now that you know the parent functions, you should be able to do all the shifts and reflections that we've done before. All right, and I want to do one last note as well. So we've been saying that a is greater than 0, and I want to address why. So let's first say that a is less than 0. And in particular, let's just say a equals -2. So then f of x equals -2 to the x. It was this quantity, -2 to the x. This function ends up being kind of crazy. So first, let's note what's happening if we're just plugging in integers. Let's say we do f of 1. That's pretty easy. That's going to get us -2 back. F of 2 is going to give us -2 squared, which is 4. So we just shifted from negative to positive. F of 3 is -8. F of 4 is 16. So when we're just graphing this, we're like bouncing back and forth across integers. So that's pretty crazy behavior already. And things get even worse when we're doing when we start doing fractions. Let's say we have f of let's just start with f of 1/3. So then, oh, actually, this will illustrate even more why. If we first start with f of 1/2, we're going to get the square root of -2, which is square root of 2 times I. Okay, so now we're popping out imaginary numbers for plugging in a fraction. But what's worse is not even all fractions give us imaginary numbers. F of 1/3 is -2 to the 1/3, which is the cubed root of -2, which exists. It's just equal to the negative cubed root of 2. So not even for all fractions do we get imaginary numbers out. Things get much worse when we're trying to evaluate at things like pi, because then how do we approximate it if it's going between negatives and negatives, imaginaries, positives? It's a disaster. So we just say that a has to be greater than 0. Then one last note, I guess I'll go to the side, is why can't a be 0? And this one, it kind of works for, well, there's 3 cases. Let's say if a equals 0. It's going to work actually fine for positives. So we have f of x equals 0 to the x. If x is greater than 0, say x equals 2, then f of x, or sorry, f of 2 equals 0 squared, which is just 0 times 0, so that's 0. That's actually fine. If x is less than 0, so say x equals -2, then f of x equals 0 to the -2, which by definition of that negative exponent is 1 over 0 squared. And now we've divided by 0. And we can't have that. So it doesn't work if x is less than 0, and if x equals 0, we get something even weirder. Then we have f of 0 equals 0 to the 0. And what should that even be? Well, 2 cases. We know that 0 raised to a power is 0. So it should be 0. But also, anything raised to the 0th power is 1. So it should be 1. And because we can't decide on this, we can't say what 0 to the 0 means. So that's not great. There actually are branches of math where you can talk about 0 to the 0. Particularly in calculus, there's this thing called L'Hopital's rule, which will tell us some cases where we can answer this. But that's for a later time. All right, so I hope that was good introduction to graphing. Remember, it's just all about these 2 parent functions. If a is greater than 1 and if a is less than 1 on the right. And then all the shifts, reflections, and transformations are just like before. All right, I think we have 1 video left on exponentials. So I'm going to end this here and make the next video. All right, see you later.